Alright guys, so let's pick up on today's lecture. So when we left off, we were talking about the Styrofoam Calorimeter and how it's a really useful tool to figure out how much energy is released by a reaction. And we said that basically what you do in a Styrofoam Calorimeter is you have a material that's reacting, it's giving off energy, and you put it into a cup of water. The water absorbs the heat that is basically given off by that reaction. And using the equation Q equals mc delta T, one can calculate the heat absorbed by the water, or QH2O, and from that you then can figure out the heat released by the system. Now the value C that goes into specific into these calculations, these calorimetry calculations, what we call a specific heat, is basically the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree. And it's something that's measured. It's measured in the lab. There are tables that describe the specific heat of all sorts of materials. This is not anything that you're going to have to figure out for yourself. These are numbers that will be given to you on the exam. Here's a table of a bunch of specific heats for several materials. I believe it's in the appendix in the back of your book as well, and you're going to use this to do some of the problems that you have to do for homework. So let's take a look at a couple of problems. We'll do example 6.1 and example 6.2 so you can see how this calculation is done. We did example 6.1 in class. It basically said, it asked for us to determine the quantity of heat that had to be added to raise the temperature of a cup of coffee that was 250 milliliters from 20.5 degrees Celsius to 95.6 degrees Celsius. And so in order to do that, you use the equation Q equals mc delta T. Now M, as we mentioned before, stands for the mass of liquid in the cup. They didn't give us a mass, they told us a volume instead. It was 250 milliliters, but lucky for us, we know the density of that liquid. It's 1 gram per milliliter, so if it's 250 milliliters, it's also 250 grams. So that's inserted in the equation in for M. Because coffee is primarily made of water, you're going to use the specific heat of water for C, and that comes off that table in the previous slide. It's 4.18. And then delta T is the change in temperature in the liquid. And change in temperature is always going to be final minus initial. And it doesn't really matter if you use Kelvin or if you use Celsius here for delta T, because the difference between 368.8 Kelvin and 293.7 Kelvin and 95.6 and 20.5 Kelvin, the difference between those values is going to be the same number. All right, so whatever you get for this, once you plug these three numbers in, you get 79,000 joules. When you have large numbers like this, you're actually better off expressing them in kilojoules. So to change joules to kilojoules, you divide by 1,000. All right, so let's take a look at another example, example 6.2, where you're going to use this equation Q equals mc delta T again. And the question reads as follows. It says, an 88.5 gram piece of iron whose temperature is 78.8 degrees Celsius is placed in a beaker containing 244 grams of water at 18.8 degrees. When thermal equilibrium is reached, what is the final temperature? All right, so basically what happens is when you put this hot iron in this cold water, the iron will release its heat to the water, and eventually they'll both come to the same temperature. So you could think of it this way: the heat or the energy that's lost by the metal is going to be equal to the energy gained by the water. And you just have to remember to change the sign on one of those values so that the math works out. All right, so how do you calculate Q? Well, the Q lost by the metal is the same thing as the mass of the metal times the specific heat of the metal times the change in temperature of the metal. And what is the heat gained by the water? It's the mass of the water times the specific heat of water times the change in temperature of the water. All right, so if we go back to the word problem and we look up what the value for the mass of how much metal they used 88.5 grams, so I substituted that in for M. If you go and look at a table of specific heats, the specific heat of iron is 0.449 joules per gram Kelvin. So iron takes in 1/10 of the amount of water in terms of energy in order to raise 1 gram of it by 1 Kelvin. All right, so you can see how high the specific heat of water is. All right, and then you substitute for delta T. Well, we don't know the final temperature, so we're going to leave that as a variable T sub F, but we're going to subtract the initial temperature of the metal, which was 352.0 Kelvin. And then over on the right side of the equal sign, we're going to substitute the numbers for water. So you had 244 grams of water in the cup. The specific heat of water is 4.18 joules per gram Kelvin. And the change in temperature, again, we don't know the final temperature of the water. It's T sub F. But we do know the initial temperature of the water, which is 292 Kelvin. And so we just substitute that in. So you work this out algebraically, and you find that the final temperature is 295 Kelvin. So these things got up to 22 degrees Celsius. All right. Now, what if you're studying a combustion reaction? You really can't combust things in water because the water puts it out. So in those cases, you're going to use something else that we call a bomb calorimeter. It's a very similar kind of a setup, except for what you have here in a bomb calorimeter is two nested cups. So you have a cup inside that's made of metal, inside another cup made of metal, and then there's styrofoam or some sort of insulation on the outside. So between the two metal cups, you have some water. And inside the first cup, you're going to have, that's where you're going to do your combustion reaction. You usually have oxygen being fed into that area so that you can get the combustion going. Now, the beauty of using a bomb calorimeter is it's used for the same purpose, is to figure out the heat that's released by a combustion reaction. But the beauty of it is that when you're given the specific heat of a calorimeter, it already accounts for the mass of water in the bomb. And actually, every bomb calorimeter has its own specific heat. It's something that has to be calibrated in the lab. And so when you're doing calculations with bomb calorimeters, it's also called constant volume calorimetry. In those cases, you don't have to account for the mass of water, so the formula becomes even more simplified. It's just Q equals cat. There's no M in the formula. So let's take a look at a problem where they have you to do you have to use a bomb calorimeter. It says octane, which is a primary constituent of gasoline, burns in air. It says 1 gram sample of octanes burned in a constant volume calorimeter, also known as a bomb calorimeter. The calorimeter is in an insulated container with a 1.20 kilograms of water inside. The temperature of the water in the bomb rises from 25 degrees Celsius to 33.2 degrees Celsius. The heat capacity of the bomb is 837 joules per Kelvin. A, what is the heat of combustion per gram of octane? Well, they analyzed 1 gram. So if you want to know the heat that's released by that 1 gram that's being burned, you just take the specific heat of the calorimeter and you multiply it by the change in temperature. So it's just 837. You notice that there is not a gram in that unit, so you don't have to account for the grams of water in the bomb. Nobody cares. It's already built into that number. Times the change in temperature, which is 306.35 minus 298.15, and you end up getting negative 48.1 kilojoules. Part B then goes on to ask, well, what's the heat of combustion per mole of octane? Well, if you analyzed 1 gram and you were able to release negative 48.1 kilojoules, in order to answer that question, all you simply have to do is convert 1 gram to mole and then divide negative 48.1 kilojoules by that value. All right, just to review, endothermic reactions, you know this already. The energy of reactants is lower than the energy of the products. The difference between this bottom line, where the energy of the reactants start, and where the top of the hump meets, that's the activation energy. So that's the energy that you have to put into a reaction to get it going. Now, half of that energy is going to be used to get particles moving fast enough to collide at the right force. And then a portion of that energy is going to be stored in bonds. So not all of the energy that you put into a reaction goes into bonds. Only part of it does. Part of it is stored. Another part of that energy that you add really goes into getting things to bounce off of each other just right. To form a product. Now, one value that you're going to start calculating is something that we call delta H. And delta H stands for the change in enthalpy. And enthalpy is basically the heat flow in processes that occur at constant pressure when no forms of work are performed. So delta H is essentially measuring how much energy is going into these bonds that are forming and getting things to collide just so. Endothermic reactions have positive delta H's, and the way delta H is related to Q is that basically it's your value for Q that you measure out of your calorimeter and divided by the moles that were analyzed in the calorimeter. There's different kinds of delta H's that we're going to talk about in this unit. There's the delta H of vaporization, which is basically the amount of energy necessary to boil water. There's the delta H of fusion, which is the amount of energy necessary to form ice or to melt. There's a delta H of combustion, which is what's measured by a calorimeter, a bomb calorimeter specifically, and then there's something else called the delta H of formation, which is also measured by a calorimeter. It's in the heat of formation is how much energy it takes to make a compound from elements. In an exothermic reaction, the energy of the reactants, as you might remember, is higher than the energy of the products. Again, the activation energy is the difference between where you start, the energy of the reactants, and the top of the peak. You'll notice exothermic reactions have much smaller activation energies than endothermic reactions. The difference between the energy of the reactants and the product is, again, this value that we call the change in enthalpy. And in exothermic reactions, that delta H is negative. Delta H, again, is your Q that you get from the calorimeter divided by the amount of moles that you measured. You'll notice if we go back to the endothermic reactions, delta H, again, is the difference between the energy of the reactants and the energy of the products. It has a huge activation energy because you have to factor in also that energy necessary to get things to collide. In an exothermic reaction, that activation energy, you don't have to worry about things colliding. That activation energy is going entirely towards breaking bonds. Okay, what do you have to know for the AP exam? Negative delta H's are exothermic reactions, positive delta H's are endothermic reactions. And you have to know how to calculate something called a heat of a reaction or heat of formation. Again, a heat of formation is how much energy does it take to make a compound from its constituent elements. Here's a sample problem that you're going to have to do out of the back of the book. They ask for you to calculate the change in enthalpy for the combustion of methane, and you have the reaction CH4 plus 2O2 yields 2CO2 plus 2H2O. There's a table in the back of the book. There's an appendix that you're going to use to solve this particular question. So you want to figure out how much energy is actually being released into the environment when you burn methane. The way that this is done is to figure out the change in enthalpy for a reaction. You do the sum of the enthalpies of the products, and you'll notice that they're multiplied by n. So you have to multiply them by the coefficients in front of the chemical equations. And you subtract from that the sum of the change in enthalpy or the heats of formation for the reactants. All right, so basically, you go in the table in the back of the book and you look up the delta H's for methane, for oxygen, for carbon dioxide, and water. And you'll notice that oxygen was 0. And that's true for all pure elements. The heat of formation for all pure elements is 0. So you look up the value for methane, it's negative 74.8. For oxygen, it's 0. For carbon dioxide, it's negative 393.5. For water, it's negative 285.83. And then what you do is you add up. You actually would have to multiply these numbers by any coefficients if that compound had any. So, for instance, carbon dioxide doesn't have a coefficient in front of it, so you leave that alone. Water has a coefficient of 2, so you multiply that value by 2. Oxygen, you multiply that by 2, but it's 0, so it's 0 anyways. And methane you leave alone. And then you would take the sum of the products, which is right down here, sum of products, and then you subtract the sum of the reactants. So the heat of reaction for this particular equation is negative 890.36 kilojoules. So that's how much energy is given off from the burning of 1 mole of methane. All right, Hess's Law. Last thing I have to talk to you about. Okay, so what if you have a mechanism? So, for instance, say I have a mechanism, and I have this equation that happens, but it happens as a series of 3 steps. And I know the change in enthalpy for each individual step, but I want to figure out the enthalpy for the overall process. Well, how do we do this? Well, we use something called Hess's Law, and Hess's Law is much like the things that we've done in the past. So you'll notice that, and I wrote this down here so you can see. Let me move this equation aside. What I look for is, I look for locations of things. So you see in the overall equation down here, carbon is on the left-hand side. Look at the elementary steps and see where is carbon. Well, carbon also happens to be on the left-hand side. So we're going to leave this first equation alone. All right. You'll notice here in the overall equation, hydrogen is on the left-hand side. So in the second equation, hydrogen is also on the left-hand side. So we're going to leave that one alone. All right, but here's the problem. In equation 3, methane's in the wrong place. In the overall equation, it's on the right-hand side. All right, but in the elementary step that they've given me, and the delta H that they've given me, it's on the left-hand side. So we're going to not use that. What I'm actually going to do is take that third equation and flip it around. All right, so that methane is on the right-hand side, like in the overall. When you flip equations around, you change the sign on your delta H. So it becomes positive 890.3. All right, so we can get rid of that third equation. If we want to calculate the overall equation for that overall reaction, then all you do is do negative 393 minus 285.8 plus 890. You just add the delta H's for the individual steps. All right, I'm done. I think you can do your homework now. If you need help, talk to me on Wednesday.